Hey guys, Miss Gosling here. In this video, you're going to learn about dark energy. By the end of the video, you'll be able to define dark energy and describe the effect of dark energy on the cosmic scale factor, otherwise known, of course, as R. So with that, let's go ahead and get started. The understandings, applications, and skills for this topic are on this screen. Take a moment, give it a read, pause the video if you have to. So I want to start by talking about the makeup of our universe. So we're kind of starting with the conclusions here. So when we talk about the makeup of our universe, for most of the year, we have been talking about the 4.6% of our universe that's made up of atoms, of the observable matter that we interact with on a day-to-day basis. We also had a video about the other 24% of our universe that's made up of dark matter. Matter that we can observe the effects of, but that we aren't 100% sure what it actually is made up of, how it works, or what laws might govern dark matter. Today, in this video, we are going to be talking about the last thing that makes up our universe, dark energy, which makes up a whopping 71% of our universe. Now, we are not going to dig into theories about what dark energy could be. Suffice to say, it is even more mysterious than dark matter. However, we are going to dig into the effects of dark energy and why we think that this thing that we can't understand or observe exists. So, when we talk about the evidence for dark energy, the key thing that we are talking about is the rate of expansion of our universe. So, as we learned previously, gravity should cause the rate of the expansion of the universe to decrease. So, our universe should start by its expansion should be decelerating over time. However, when we look at our Type 1a supernovae, one of our favorite standard candles in the universe, what we see instead of our universe slowing down, we actually see that its rate of expansion is increasing. So our universe is actually accelerating in its expansion. So something needs to be responsible for that acceleration, and that something we call dark energy. On the left, you can see a graph of the expected rate of expansion for our universe, that black line, versus the actual rate of expansion that we are observing in our universe. So the model that we've built using dark energy. So what is dark energy? Again, like dark matter, we don't know. And we know even less about dark energy than we do about dark matter. We don't even have categories of potential candidates for dark energy. So we don't know what it is. But what we do know, one, we know it fills our universe. We know that it results in a force that opposes gravity, that causes our rate of expansion to increase. We know it makes up 70% of the universe because that is what our observed rates of expansion for our universe show. And we know that it's causing our universe's expansion to accelerate. So with that, let's go ahead and work through an example problem. Take a moment, read the question, and pause and see if you can solve this problem on your own. Once you have, we'll go through it together. But again, pause. Try it yourself first. So I hope you've all enjoyed trying to solve this question. Let's go over it together. So first, when we look at the rate of expansion of the universe, we get a curve that looks something like this, where our rate of expansion increased, it's kind of smoothed to where we are now, and then has continued to increase once again. Something that looks vaguely like, as long as we see that increase up here, you'll get those marks. But that's what we're kind of looking for. We want to see that you understand that the cosmic scale factor is increasing the rate of expansion of the universe. Part 2, we're talking about the variation of temperature versus time for the two models. So we know that temperature is going to be proportional to 1 over r. As our volume of our universe increases, the temperature of the CMB will decrease. We've seen that when we look at the cosmological history of the Big Bang. But we can also see this when we understand thermodynamics, right? As volume increases, so as for us the cosmic scale factor increases, the temperature of the cosmic microwave background is going to decrease. And for both models of the universe, our temperature is going to decrease because our cosmic scale factor is going to continue to increase. However, in the accelerating model of the universe, so in this model of the universe represented by the blue line, that model of the universe with dark energy, the temperature is going to decrease faster because R will increase faster. So with dark energy, the rate of expansion of the universe is bigger, so R is bigger. Thus, T will decrease more quickly. You will note 2 points, 2 marks, compare here, contrast here. Look at how the way the question is asked tells you how to answer it. Okay, so that brings us to our takeaways. First of all, like dark matter, we don't precisely know what dark energy is, but we can observe its effects. And specifically, the effect we can observe is when we make a graph of the variation of R versus T for a flat universe, we see that rather than the rate of expansion of our universe flattening out, we instead see that the rate of expansion of our universe is accelerating. Second, type 1a supernovae were critical to determining that our universe's expansion is accelerating. This is because they are standard candles, so they help us figure out. So they have a known luminosity and they have a known brightness, so we can figure out how far away they are, and we can figure out how quickly they're receding by measuring redshift, and so we could see does the redshift match what we expect it to be. And finally, approximately 70% of our universe is made up of dark energy. I'm just going to highlight that whole last bullet point because that's very important. So with that, you've learned about the second mysterious thing that makes up the vast majority of our universe. I hope this was interesting. I hope this has sparked your curiosity into modern physics research. Best of luck and happy searching.